Today we will be presenting Lesson 2 on AP Chemistry. In this lesson we will focus on atomic structure and electron configuration. Welcome, fellow science enthusiasts, to the mysterious universe of atoms. Imagine an atom as a bustling city where electrons are the citizens, living in different neighborhoods, or as we call them, shells, subshells, and orbitals. Each shell is like a concentric circle around the nucleus, and subshells are sections within these shells. Further, these subshells are divided into orbitals, the individual homes of the electrons. Now, our electrons are orderly citizens. They follow the Aufbau principle, a rule that dictates how they fill up their atomic city. Picture this: you're at a concert. The rule is, you fill up the seats from the front, right? Same with electrons. They fill the energy levels from the lowest to the highest. But wait, there's a twist. Sometimes an electron in a half-filled or filled orbital gets a little adventurous and decides to move to a higher energy level. It's like ditching a half-empty concert to go to a full-blown party next door. That's the Hund's rule for you. And then there are ions, atoms that have gained or lost electrons, altering their electric charge. So, how do these ions configure their electrons? Well, if an atom loses an electron, it loses it from the highest energy level, not the outermost shell. On the other hand, if it gains an electron, it adds it to the outermost shell. Think of it like a city undergoing a population change. If people leave, they leave from the highest floor of the tallest building. If new people arrive, they occupy the outermost areas of the city. So there you have it, the basic structure of an atom and the fascinating world of electron configurations. It's like a cosmic dance, with electrons twirling around in their atomic city, each following the beat of the Aufbau principle and Hund's rule. Now that we've cracked the code of electron configuration, let's move on to something even more exciting. Next, we're going to take a grand tour of the periodic table. Not just to admire its colorful blocks, but to understand the trends among elements. Our first stop on this grand tour is Coulomb's law. This law is like the rule book for how charged particles interact. It says that the force between two charged particles is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. In simpler terms, it's like a cosmic dance where particles are attracted and repelled based on their charges and the distance between them. Next, let's explore the concept of atomic and ionic radii. Think of the atomic radius as the size of an atom, while the ionic radius is the size of an ion. These sizes can change based on the number of electrons an atom gains or loses. It's like a cosmic game of tag where atoms can become larger or smaller depending on how many electrons they tag on or let go. Moving on, we encounter ionization energy. This is the energy required to remove an electron from an atom. It's like the price tag on an atom's electrons. The higher the ionization energy, the higher the price to pluck an electron away. Next up is electron affinity. This is a measure of how much an atom wants to gain an electron. It's like the desire of an atom to add to its electron collection. The higher the electron affinity, the more eager the atom is to snatch up an electron. Last but not least, we have electronegativity. This is a measure of an atom's ability to attract bonding electrons. It's like the charm factor of an atom. The higher the electronegativity, the more charming the atom is to electrons. Well, that's a wrap on periodic trends. Remember, these trends are your cheat codes to the periodic table. Ever wondered why some atoms are more sociable than others? Well, it's all about their valence electrons. Picture this: it's a Saturday night and you're at a party. The atoms are the partygoers, and the valence electrons are like the atom's social skills. The more valence electrons an atom has, the more likely it is to interact with other atoms. It's as simple as that. Valence electrons reside in the outermost shell of an atom. They dictate the atom's behavior because they are the ones engaging in chemical reactions. Just like the life of the party is the one likely to start the dance off. Now let's talk about ionic compounds. These are formed when atoms, driven by their desire to reach a stable electron configuration, decide to exchange valence electrons. This is like trading dance partners at our party. Some atoms, like metals, are quite generous and readily give up their valence electrons. Others, like nonmetals, are more on the receiving end. Take sodium chloride or table salt, for example. Sodium has one valence electron it's eager to part with, and chlorine is more than happy to accept it. This exchange results in both atoms achieving a stable electron configuration. Sodium becomes a positively charged ion, and chlorine becomes a negatively charged ion. Opposites attract, so these two ions stick together, forming an ionic bond and creating the ionic compound known as sodium chloride. It's important to remember that not all atoms are as sociable as sodium and chlorine. Some atoms prefer to share their valence electrons rather than give them away or receive them. But that's a story for another day. So, the secret to an atom's social life lies in its valence electrons. Intriguing, isn't it? Now let's take a peek into the fascinating world of photoelectron spectroscopy. Imagine being able to take a snapshot of an electron in action. That's essentially what photoelectron spectroscopy, or PES for short, allows us to do. It's like we've been given superpowers, able to see the unseen and unravel the mysteries of electrons. So, how does this superhero of a technique work? Well, it involves shining high-energy light, often X-rays, onto a sample. This light is so energetic that it can knock electrons right out of the atom. These ejected electrons, known as photoelectrons, are then measured for their kinetic energy. Now, here's where it gets interesting. The energy of the incoming light minus the kinetic energy of the photoelectron equals the binding energy of the electron. And this binding energy is the key. It gives us information about the electron's original energy level in the atom. But what does this have to do with electron configuration, you might ask? Well, remember the Aufbau principle from earlier? The idea that electrons fill up the energy levels from lowest to highest? Photoelectron spectroscopy provides the experimental evidence to back this up. When we look at a PES spectrum, we see peaks that correspond to different energy levels in the atom. The higher the binding energy, the closer the electron was to the nucleus, and the more tightly it was held. This means we can identify which peaks correspond to which shells and subshells in the atom. So, in essence, PES allows us to build a picture of the electron configuration, but in reverse. We start with the highest energy levels and work our way down. It's like doing a jigsaw puzzle, but with electrons. And that, my friends, is the magic of photoelectron spectroscopy. It's not just a technique, it's a window into the inner workings of atoms, allowing us to literally see where electrons reside within an atom. With photoelectron spectroscopy, we can see the unseen and unravel the mysteries of electrons. Pretty cool, huh? Well, it seems like we've covered quite a bit of ground today. We've journeyed through the intricate world of atomic structure and electron configuration, learning about shells, subshells, and orbitals, and how they form the blueprint of an atom. We've seen how the Aufbau principle guides the arrangement of electrons, and how ions are not just rebellious atoms that have gained or lost electrons, but have their own unique electron configurations. We then ventured into the realm of periodic trends, where we discovered that the periodic table is not just a pretty poster on your chemistry teacher's wall, but a roadmap of atomic and ionic radii, ionization energy, electron affinity, and electronegativity. We learned that Coulomb's law isn't just a fancy physics term but a crucial player in understanding these trends. Next, we dove into the world of valence electrons and ionic compounds. We found out that valence electrons are the social butterflies of the atomic world, always ready to interact and form bonds, giving rise to ionic compounds. And let's not forget, these compounds aren't just the salt on your fries, but they're essential to many chemical reactions. Finally, we delved into photoelectron spectroscopy, a technique that might sound like a sci-fi gadget, but is actually a powerful tool in the world of chemistry. It's through this method that we can see the energy levels of electrons, giving us a deeper understanding of atomic structure. Each of these topics forms a crucial piece of the AP chemistry puzzle. They're not just isolated facts to memorize, but interconnected concepts that help us understand the fascinating world of atoms and their behaviors. As you move forward in your AP chemistry journey, remember to revisit these concepts, as they will continue to pop up in many different contexts. Thank you for watching this video till the end, and I hope you found it helpful. I'll see you in the next lesson.